Okay, so in this class, we also have an exam on Friday. And the topics for that are everything up through structures. So what could I give you on a test that wouldn't show up in a structure? Vector stuff and particle statics. Remember that if you're doing statics of a particle, you're treating something as a particle. You're not using the moment equation. You're only using Newton's laws. In 2D, you'd have the two components of Newton's second law. In 3D, you'd have three components of Newton's second law. Okay. Those are the only two things besides structures that don't show up in structures calculations. But probably it's going to be structures. It's going to, I might ask you a quick question on this or a quick question on that, but mostly it's going to be just knowing where you're at with structures calculations. All right, just remember it's cumulative. So if I wanted to put vector stuff, there's nothing legally preventing me from doing that, or particle stuff. Okay. Anybody have any homework questions or anything like that? All right. So the thing we were doing last time, we're getting into internal loads. And so I'm going to finish the example that we started last time.
If there's a centroids problem in the exam with like calculating the center of mass, I think will we be given like the formula for it?
Yes, you will. Yep. That's a good idea. I hadn't thought about that. Yeah, you had a structure too where you had to calculate the center of mass to apply the weights, right?
Yeah, I'm thinking of like the assignment. I think there's like a semicircle in that one. I forget.
Okay, right. That's right. That's right. That's right. Yep. Okay, so the example we did last time was like this. We have a horizontal beam. At the middle, we have a roller. External loads at the end of 500 newtons and 1,000 newtons.
I have another question.
Yeah.
So we can flip which way we make the cuts, or like our sign convention or whatever.
Yeah.
When is it more convenient to do that? Because we've only ever done it where our cut's on the right side and we're going left to right.
Yeah. I don't think there's ever any reason to do that, really. It's just, really, I only brought up that possibility to point out why we didn't just keep using vector sign conventions for the internal loads. Because then you'd have this indeterminacy, like what are the internal loads at this point? And you'd be like, well, if you do it from this side, they're this. You do it from this side, they're this. It sort of means the same because it's Newton's third law. You'd really just like to have a thing where at this point, these are the internal loads and that's the end of it. This whole thing is 3 meters long. So each of these is 1.5 meters. And the mass was 100 kilograms. And we're trying to calculate the internal loads. So after we calculated the external loads, we got a thing that looked like this. 1,000 Newton force that way, and a 500 Newton force down. That distributed load is 981, the total weight divided by the total length. So we got a uniform distributed load with a magnitude of 327 newtons per meter. We had a force from the roller of 1981. And then over here, we had a 500 down and a 1,000 this way. And so the cuts happen between these 3 points. So the right end of each cut, is going to be between these red marked loads. That means since there's 3 of those, we have 2 cuts. And for cut 1, that's valid for x's between 0 and 1.5. We had T equals 1,000. V equals negative 327. 327x minus 500. And a bending moment of negative 163.5 x squared minus 500x. We've talked about the fact that you should always be able to take the x derivative of the bending moment and get the shear force. There's something else brewing here that isn't as obvious to see, but if you take dv dx, you get, negative 327 in this case. Our q function is 327. It's positive, but that's because we're considering a positive q to be down. So that sort of flips the signs of this relationship. And so that shear force, negative dv dx, is always going to be equal to the total distributed load function. Okay? So again, like if you had a beam and you had distributed loads, instead of going through Newton's laws, you need them to calculate the external loads, but you could just straight integrate the distributed load to get the shear force, then straight integrate the shear force to get the bending moment, if you knew how to deal with the boundary conditions, which can be sometimes a major pain, but so what we're going to do anyways is we're going to keep using Newton's laws, calculate these things that way, and then use these as checks on our work. Okay, so cut 2. This is for x's between 1.5 and 3. We have the 1,000 Newton force horizontally, the downward 500. Now we have this upward force of 1981. The distributed load with a uniform value of 327. And then we haven't gotten all the way to the end, so now we just have the internal loads. And the distances These two are 1.5 apart. That doesn't depend on X. You know, you're not, by choosing a different value of X between 1.5 and 3, you're not changing where that roller is. That roller is just always 1.5 meters away. And then this is X. So what do we know about this rectangular shaped distributed load? We know it has a length of X, a height of 327. Its centroid is right in the middle. So the distance from the left end of that rectangle to where that centroid is X over 2. And the area, the total point force, is 327 X, because it's just the area of that rectangle. And so now I'll draw this again. So all of the things that are point loads just go back in here. But now we're going to represent that distributed load with its point force. That's a downward force of 327x. And the distance is this is X over 2. This is 1.5. And this is X. Okay, Newton's second law says negative 1,000, negative 500, plus 0, negative 327x, plus 0, 1981, plus t negative v is zeros. So t is equal to 1,000. V is equal to negative 327x minus 1481. Yeah.
Should that be positive 1481?
Yes. I just hadn't written this yet. And then the moment equation. So you have a clockwise moment with a force of 327x and a moment arm of x over 2. Counterclockwise moment with a moment arm of 1.5 and a force of 1981. Then plus m minus vx is equal to 0. So m is equal to v times x plus 163.5 x squared. 1.5 times 1981. minus 2971.5. Now plug in V, what we know for a function for V in for the V here. And we get negative 327x squared plus 1481x plus 163.5x squared minus 2971.5. We have two x squared terms, and so they come out to be negative 163.5x squared plus 1481x minus 2971.5.
Shouldn't that be positive? 2971.5. It's positive 1.5 times 180.
Yeah, but then you have to, then you get m by itself.
Oh,
So you solve for, yes, I got one.
I get you.
Okay. Okay. So anyways, there's the two functions. And I'm not going to plot those, but let's check the derivative things. So we just talked, we know that dm dx has to be equal to v. So negative 3, take dm dx, you get negative 327x. That term matches. Plus 1481, that term matches. So that's good. So now let's think about the distributed load. Negative dv dx, and remember the negative is because our definition of that function q, that distributed load function, is down. That's the default. So you just get negative dv dx is positive 327, and that's our distributed load function. Okay? Okay, so now, this is the last little wrinkle. So now what about something like this? Let's start with a cantilever beam. And the only external load on it is a distributed load with a triangular shape. Let's make the length of this 1.5 meters. And let's say that the height of the distributed load at its highest point is 3,000 newtons per meter. First thing we have to do is calculate the external loads. So free body diagram of the whole thing. It's a fixed joint at the wall, so call that R and a couple of MR. That distributed load has a length of 1.5, a height of 3,000. The centroid is a third of the way from the perpendicular side going towards the point. So this distance is 1. The area is 1.5 times 3,000 divided by 2. And so that is 2250. And so I'll represent this as a downward force of 2250, where this distance is 1 meter. And there's nothing else going on. I'm ignoring the weight for now. So Newton's second law says Rx, Ry plus 0, negative 2250 is equal to zeros. So that reaction force vector is 0 for X, positive 2250 for Y. And then the moment equation, I'm going to use this as the about point. So we have that external couple, MR, and then the 2250 would produce a clockwise moment, so that's negative, with a moment arm of 1, a force of 2250. So the couple is positive 2250. Does that make sense intuitively? Well, that 2250 you can tell is gonna try to make it rotate clockwise, and so in order to counteract that, the wall has to apply a counterclockwise moment to it, and so that's going to be positive. So yeah, that makes sense. Okay, so now things are going to get ugly. There's the two endpoints, and then in between them, there's nowhere where that distributed load function changes. Okay. And there are no point loads. So, okay, one thing I'm going to do before I start this is I'm going to come up with the function Q. So what's the function Q of X in this case? We didn't have to worry about that with uniform distributed loads because it's just a constant function, right? So whatever it said on the picture, that's your Q of X. But our function now isn't 3,000, right? We want a function that tells us what the height of that distributed load is at any X value. And obviously that's not it, you know? So how are we going to come up with this function? We're going to calculate the equation for that line. Okay, so if you think of your coordinate system like this, when you get out to a value of 1.5, you have to be at a height of 3,000. So we're going to just use the y equals mx plus b form. Someone tell me what b is, and then you don't have to answer anything else about this whole problem.
Zero.
Yeah, you got it. You still have to answer stuff. Okay, and now what's the slope of that? Just rise over run, so 3,000 over 1.5, so 2,000.
For Q of X, do our units mean anything? Because now our slope has gone to be newtons per meter squared.
Our slope, So yeah, it's newtons per meter squared, but then you're multiplying it by x. So you get newtons per meter.
Okay.
Yeah.
Okay.
I must say, I sort of stopped thinking about the units with this kind of stuff, but they do work out, but I don't think it helps much to think through the units as you're doing this. Okay, so 2000x, that's our function. And that's q of x. So we expect to have our shear force function be something related to 1000x squared, negative 1000x squared, I guess, right? Because of the derivative relationship. Okay. So now we'll do our cut. First, there's only one cut, and it's for all the x values between 0 and 1.5, not including the endpoints. And I'm going to go back to drawing the stuff that we are including and the stuff that we're not including. We have a force of 2250. And a couple of 2250. And then we have this distributed load. Give myself a little more room. Well, this is for a general distance x from the left end. And what's the height of that triangle at the right end? It's not 3,000 because the 3,000 is over here off of what we're considering. Okay. So if you go out a distance x, what's the height of that?
Y.
Yeah, exactly. So the height here is 2000x.
Q of X, I guess.
Okay. And then we have the internal loads. So now to calculate the centroid and the point force, we have a width of x, a height of 2000x, the location of the centroid is 2/3 x. And the area of that triangle is 2000x times x over 2. So 1000x squared. So I'll redraw the free body diagram. We have the force of 2250, the couple of 2250. And now that we've chosen the body to isolate, now is when we can represent that point force, that distributed load as a point force. Like notice everything would have been different if we would have done this whole problem calculating internal loads based on that first substitution of the distributed load for the point force with the point force. Okay? We'd get the wrong answer there. Each time you draw a new free body diagram, you have to do a new determination of what is the point force that represents that distributed load. Okay? So now we have this downward force of 1,000 x squared, and the internal loads Newton's second law says 0, 2250 plus 0, negative 1,000 x squared plus t negative v is equal to zeros. So t is 0. V is equal to negative 1,000 x squared plus 2250. And so negative Vx, negative dV dx is 2,000x. And then the moment equation the about point is there. So we add on the couple, 2250. This moment arm, we figured out from that triangle picture, is 2x over 3. That is a clockwise moment, so we have minus 2x over 3 times the force of 1,000x squared. Then we have plus m minus vx is equal to 0. So m is equal to positive 666.6 repeating x cubed plus vx minus 2250. So m is equal to 666.6 repeating x cubed minus 1,000 x cubed plus 2250 x, because I'm multiplying that whole v function by x, and then minus 2250. And so m is equal to negative 333.3 repeating x cubed, just combining the two cubed terms, plus 2250 x minus 2250. So we know that negative dV dx is equal to that function q, so that's good. That needs to be the case. Dm dx is equal to negative 1,000 x squared plus 2250, and it's equal to v, so that's good. Any questions about that? Okay. I want to show you something, but we're not going to do this calculation. Here's an example we won't do. Okay, let's say we have a beam that's cantilevered over here. That's just so we don't have to calculate the external load, so I don't waste a ton of time on this. And let's say we have a triangular distributed load like this. It doesn't matter what this is. Let's say this thing is 2 meters long. Okay, so it's pretty much the same thing as the last one we did, right? So, but let's think about what happens when you start making cuts. So this is valid for x's from 0 to 2 meters. So our cut includes this piece. And it doesn't include that piece. So there's this stuff going on at the wall that we don't have to worry about. But now look at this triangle. This is a fiasco.
Not even a triangle anymore.
Exactly. That is the problem. It once was a triangle, but now it's a trapezoid.
It's a shell of a triangle.
Yeah. Yeah. So let's see. Well, the one thing that's nice is we do know the height of it over here, you know. Could you calculate this? Yes, you could. You could break this up into okay, so it's a frickin' trapezoid. Here's you. So to do this calculation, you could break it up into a rectangle and a triangle.
Base times average height. Height 1, height 2, divided by 2.
No. You'd have to come up with the function for the, you'd have to come up with the Q function, the function for that line, and that would be the height of that rectangle. And then the height of the whole thing would be 2,000. So this would be, 2,000 minus Q. And okay, it would be a pain, right? This you can do. But it's a pain. So what would you do if you see a triangle oriented in this direction?
Flip your paper over and go through the.
Yes, that's exactly how to, yes. Walk to the other side of the beam. And then you have the problem we just did. and it's much better. Okay. Also, this is one where you could work from the right side, you know, if you didn't feel like walking, you know, like maybe the beam's really long, you don't want to walk to the other side. You could work from the right side, but I think it's easier to just picture what's going on from the other view. Okay, so we have to do one more example, and that's one where we have this triangular distributed load and also a weight force. Okay. So let's say we have a beam like this. The triangular distributed load is this way. Let's say that that's 1,000 newtons per meter at the highest point. And let's say that this is 3 meters. And let's say that this time the mass of the beam is 3 meters, let's call it 50 kilograms. Like I said before, you can calculate this without first figuring out the external loads. So we can just sort of go right into the cut. But I want to show you a free body diagram of the whole thing because it sort of illustrates what we're looking at. So we have this distributed load. And then we also have this one. And we can think of these as being the shaded part is the beam. Okay, so we can think of this as being two separate distributed load functions. I'll call this one Q1. And that one's easy because it's just uniform. So we have 490.5 divided by 3. So 163.5. For this one, we have to figure out the function for that line. I'll call this one Q2 of x.
33.3.
Right, yep. So just the slope is going to be 1,000 divided by 3. So 333.3 repeating x. And so the total distributed load function is just going to be the sum of these two. So 333.3 repeating x plus 163.5. And so we're going to expect our leading terms of our shear force to be 166.6 repeating x squared plus negative 166.6 repeating x squared minus 163.5x. Okay. You don't have to think about that yet, but if it doesn't come out that way, then the derivative thing isn't gonna work, you know. So remember that if you have multiple distributed loads, the Q function that you're talking about is the sum of the two functions. Okay, let's stop there and I'll do this problem next time.
V is always an order higher than the Q function.
What?
The shear function is always an order higher than that.
Yeah, exactly.
Like a parabolic
That's right.
distributed load of V.
That's true. Yeah, so if you, not with sinusoidal functions, but not with exponential functions. But yeah, all we're doing is polynomials. So yes, with polynomials, that's right.
You better hope it's a short beam if you have an exponential distributed load.